This video describes the fitting of the number 7 Quasar toric lens through the Medmont E300 corneal topography fitting software. Start with a good quality image, then go to the Home tab and contact lens icon. Select from the design menu the number 7 Quasar. Enter in your Spectacle RX and vertex, then click OK. You can alter the lens diameter as required based on your measured visible iris diameter. Then click on the edge of the contact lens and center it to what you feel is the geometric axis of the eye. In other words, center the contact lens as you would like to see it centered through the slit lamp. Then click your cursor in the center over the center pink dot, which is the geometric axis of the contact lens. Measure the TFC or tear film clearance. In this case, we predict to have 0 microns of fluid between lens and cornea. Clearly, a steeper base curve is required. Let's therefore steepen the base curve a couple clicks and apply. That takes us to 16 microns. Ideally, we're looking for very close to 20. Let's try another quarter step or 0.05 millimeters. This takes us to 24 microns of fluid between lens and cornea, and this is quite optimal. We have good healthy landing at 3 and 9 o'clock. However, the amount of fluid running through the vertical meridian is excessive. When we click our cursor here, we're at 58 microns. Click our cursor here, we're at 75 microns. So before the peripheral curves kick in, we're well above the optimal 40 micron threshold of fluid between lens and cornea. In other words, when your fluid layer at the edge of the optic zone junction or just before the peripheral curves kick in is in excess of 40 microns of fluid, in this case somewhere around 60, on the opposite side somewhere around 80, this will create an unacceptable amount of rocking of the lens back and forth, instability and discomfort for the patient. Let's therefore select the toric option and apply. This creates now a radius across the flat meridian and a different radius across the steep meridian, a bitoric lens. The next step is to measure the apical clearance. Make sure we're very close to our target of 20. In this case, we are. Then look for the axis of greatest bearing, and it appears that running through the vertical meridian or close to the vertical meridian, we have our landing at 12 o'clock and our landing at 6 o'clock. So the path of least resistance of the lens may be nasal and temporal, while its movement vertically and healthy tear pump may be hindered by the bearing at 12 and 6. Let's take our flat meridian, the blue line, and attempt to steepen the lens so it will land across that horizontal meridian. Let's apply our change. See if we can move that bearing around. We'll try another 2 clicks. Now we're starting to get the lens coming around the corner and landing closer to 3 and 9 o'clock. When we click our cursor in the center, we've now increase the apical clearance to 38 microns. Let's flatten both the flat and the steep meridian equally. See if we can reduce that down to close to 20. Now we have the target amount of fluid at the apex of the lens, and we have landing very close to 3 and 9 o'clock, which is optimal. This should keep the lens on lateral center. Then running through the vertical meridian, we have a fairly linear fluid layer. Possibly we could reduce a little bit of this fluid near 12 and 6 o'clock by steepening the steep meridian by itself. And that's creating a little flatter of a line or a more linear relationship between lens and cornea. Let's try one more click. Now we see a much more straight line surface. This gives us landing close to 3 and 9 o'clock and a good channel running through the vertical meridian. So find that ideal point where you've landed the lens as close to 3 and 9 o'clock as possible while having that healthy channel running through the vertical meridian. Then once you've created that optimal pattern, you can order those final parameters from the lab here under the lens parameters window.